industry. And this is presented, prepared by some people from Min University. So first, some of you know where the Professor Hyung Kim is chairman of Korean CAPI, and he is coordinating all the ISO standards activity for Korea. To save time, I'll move on next one. It's a skip already, you saw it. Anyway, I can say it's probably I'm one of you, if not the only one, to work with three most comparable largest company in the world, like Procter & Gamble, Kimberly-Clark, and Georgia-Pacific. It's a very strange that I have experienced. And I'm working for Korean University. And here we have a special PhD student from Indonesia. Her name is Lily Melanie. She's here somewhere. Has a very nice correlation, cooperation between Indonesia and Korea. And we have another PhD student, Nayampa and Hyung-Lee. They all, Lily Melanie will present for this afternoon session, and the two other folks will present the posters. So please come to their nice presentation. Actually, in the paper industry, as you know, we can divide the two areas, like high density and high basis weight, like the printing paper, paperboard, all those stuff. And another one is hygiene paper, which is low density and low basis weight. They are only common is they using cellulose fiber. Other than that, they are totally different animals. Okay, so when you learn from one thing, apply to another, you'll have a disaster. Okay, so it's dealing with totally different structure, I can say. So these are products. And as you see, surface roughness, surface characterization is critical to like printing, coating, laminate, or adhesion in industry. Also, in the important hygiene paper like tissue softness or absorbency. This is for paper industry people. We're talking about application of surface characterization, but as a matter of fact, any phase to material dealing with surface characterization is so important, like electronics, the nano coating, all that area. Particularly if you go 3D printing, the control the surface roughness is so critical. I'll go into that stuff more detail later. Okay? So in the one area is surface roughness friction determinant area. This is more like art rather than science. A lot of people packaging on paperboard and dealing with surface roughness, but very few international standards exist at present. So actually, I'm in charge of the surface roughness in paper, pulp and paper as a convener. So in the future, I will be more actively involved in standardization of it in this area. Hopefully, we can work all of you together. Then, as you see, surface roughness consists of two areas, like a surface roughness or like a topography, how high valley peak looks like, that kind of stuff. You can see image, all the nice stuff. So there are several ways to measure surface roughness. One is the so-called non-contact method, like the image analyzer you see. Most of it is easy to use, analyzers are most widely used at this moment. Another one is indirect method, because they don't measure surface roughness directly, but measure physical property, and you know reference sample what the relative roughness is. It's called the indirect method. Another is a contact method, which really probe dealing the surface, how feel the roughness, the friction. That's called the contact method. And in the case of the surface friction, obviously you have to touch the sample. Without contact, you cannot measure friction. So contact method is only useful, but so far, not many instruments are commercially available to measure surface friction. And I may say here, there is no ISO standard on surface friction measurement, no contact method. even for surface roughness, there is no contact method available because I think we don't know how to do it. That's hopefully it's a great chance to work in this area. So this is just a commercial instrument because but if you don't have a higher standard doesn't mean no commercial instrument available. Actually, strangely enough, there is supposed to have a commercial instrument. They start to put those ISO standardization to justify using of that instrument. Okay? So, for example, this is the optical method, and this is a commercial unit called optical from Lawrence to Sweden. It's a part of ABB. Next one. So another is indirect method. It's a major so-called Ehrlich method. So we have 5 ISO standards at this moment, and 3 already in ISO standard, 2 like a print soft, and Oken method is now in progress. I'm in charge of pushing these 2 for ISO standard. And Oken method actually, Professor Enomar is leading this project. Okay. So this is an instrument that looks like it's an instrument, commercial so no big deal here. So now, as I said, surface friction is no ISO standard available. So far, only way to measure friction is coefficient friction and its variation, nothing else. So actually, you measure it, you don't know how to use it. That's the current situation. Okay. That, for example, I put the commercial instrument there, and no information about structure. Hey, there's a low coefficient friction. Question so what? Then they don't know what to answer. Next one. So to summarize the current status, pure already the industry standard exists. That depends on their needs. There's nothing wrong about that. Each people manufacture their own needs. So they use their own method. That's one of the reasons why we don't have a standard yet. That means there is no direct comparison possible when they're reporting some values. Also, that's what I'm saying, I mean, kind of a responsibility and kind of honor to push through the surface line characterization as a future science and technology. So, summarizing current status of surface characterization, the results depend on test method, everybody knows. Means also, even with all different instruments, they generate different results. Not only that, even the same method, depending on test conditions, they have a different result. So depending on, hey, we use the same instrument, how come your numbers are different? Because the operating conditions are different. So there is another problem here is no clear linking between surface characterization and probability. For example, hey, we measure the surface roughness here. So what about printability? Is it good or bad? We don't know, but we just try that. That's what we have been done for so many years. I worked for tissue industry over 30 years. That's a typical way. We measure, hey, this is a little better load formation, better formation, low roughness, but we don't know about printability. Another is that now another real problem here is that when you measure any kind of thing, they report as average value and coefficient variation or standard deviation. That's the measure uniformity from sample to sample. Does not say about the characteristic structure. Okay? So I'll show you later. So even you have the same average, same coefficient variation, physical property can be totally different. That's what we need to think hard. What are we going to do with this average value and coefficient variation? So now the question is, then what we have to do all the questions. Yeah, you said a lot of questions. So what? How can handle? That's not good to answer those questions. So like here is one of the good examples. Here, obviously you see from A and B sample, one is a very smooth contour, feel like smooth, one is very sharp. The problem is when you measure surface roughness, they generate the same average thickness and coefficient of variation. But how do you expect from this profile they should have the same physical properties? Okay? This is a typical wearing, all these all the problems. Hey, we have the same numbers. And this sample is very difficult to laminating. That's the answer. Hopefully you appreciate the same average coefficient variation is not enough practice handling in real situation. Another good example is this cartesian is very famous from Procter & Gamble about Shannon product, Shannon tissue. You see that they intentionally generate a high free fiber top. Obviously, their structure will be very high roughness, okay? But that's the feel people softer. That means that now another question is how this guy have a high roughness about a higher softness, because the structure is different and we don't know what to measure for average roughness. That's another question. Okay? So that's what you see so far. Even same average or same correction variation, they can have a totally different printability or wearability and also softness capacity. So to summarize so far the current status, the average value without understanding of structure can really wrong conclusion. Okay? That's so critical. We need to understand what we measure, what we mean by average value to coefficient variation. That might be a very limited case for process control, for example. Maybe average coefficient variation might be enough. But change your furnish, change process, then you think it's hard. Why? Well, what's the origin of this variability? That kind of stuff. So already I hope you're convinced that same average variance and coefficient variation may be trouble rather than solve the problem. So now, to handle this one, I realized that you really measure friction, because that's really tell how you feel or printability, variability. As you see, all these are physical measurement. The wearing, you need the interaction. Printability, you need coating, everything need physical interference. Okay, that's to figure out any correlation. You need to measure friction, actually contact method. So far, actually, only instrument can do this kind of testing is Gato test, KS test. I'll show you briefly more about this one. So first evaluation of Gabara. I think Gabara's test is very well known, having used over years in textile industry to measure a handful of fabrics and non-wovens. They have like 4 units called tear test, bending test, compression test, surface test. Okay. Then they have a very nice correlation, multilinear regression so-called. They put the 16 parameters to figure out which is the best fit in the handful of subject evaluation. One thing here, the problem is multilinear regression is after fact. Doesn't say why they have a high correlation, then how to fix it, just to show correlation. Recently we published one paper in Nordic and Pulp paper. One thing we really killing us, based on our model is based on R-square numbers. Totally can be wrong. So that's why we need to think hard to develop a model based on R-square numbers. Okay? Then one thing really nice thing about the KS system is a surface test. Then here I really like Professor Gabara. He's the first in the world thinking that deviation from average is more important than just the average, the thickness or the standard deviation. So we call the SMD, mean deviation. Here, deviation is different from variation. Variation means uniformity from sample to sample. Derivation is how profile is changing along the line. Printability is you're talking about one scaling area, not talking about from sample to sample. Okay? So Professor Gabara saying is when people feel, then you need a constant controlled structure, not uniform structure. Okay? So particularly it's very important in coating industry. You don't want to necessarily the smooth surface, but control structure. That's what really help the printability, that kind of stuff. That's what Professor Kawara claimed, Boston claimed, that mean deviation is so critical to measure hand track, and we already see that's true also paper and paperboard. So, okay. How do you show the very long history? Alphabet for surface test is developed in early 1970s, 80s for textile industry. We are the first one tried the tissue for interval, but that's myself there. We're working very closely with Kawara to develop a surface test for tissue. Actually, that's why I work for Georgia Pacific, and we work over 4 years in Kawara. That because of our contribution, with the Silver Key Award, that is our distinction award from Georgia Pacific. Okay? Then, from based on it, took about 4 years from that old style to second generation surface test. Okay? Next one. Now, we are also very closely working in Kawara. Now we call the third generation. Third generation is, you see, now we have a data logo is acquire data more point. Previous Kawara data is collected only about 200 points. Now using this data logo, you can get about 2,000 data, about 10 times higher. That allows us to do all the profile analysis. Another thing is we realize that depending on style shape, they have all different results. Also, that means depending on paper grade, writing paper, paperboard, liners, you have to use different styles depending on your need. Your size, ink, printing, whatever, you have to select the right stylus. But this is third generation Kawara allow us to change the stylus whatever you want. And as I said earlier, as the convener of Working Group 25, we're making some standardization of surface roughness or different stylus at this moment. So here is the roughness profile. You already see nothing more than just the roughness, there's the skin length, how the fluctuation. So far, as I said, we look at the mean, average, and standard deviation from sample to sample. But this is a formula how to calculate mean deviation of the roughness and friction. Okay? Next. So there is one classical example is principle we call the Richardson problem. That is, what's the length of coastal line of Britain? Answer is depending on what ruling size measure is. If you're in a final rule, you're going to larger. And it's strange, because it's hand coastal length cannot depend on its measuring size. Okay? That's the Richardson problem. So later he said, hey, as a ruling measuring ruler is going smaller, the length of the coastal line goes to infinity. That's a very important concept. Is how can come England areas doesn't go infinity, that's same infinite area. How within finite area length can go infinitely long? That's a classical problem. So that's why now later here like that Richardson said, hey, the Mandelbrot was saying is when you plot against the lower coastal length against the resolution, they have a linear relationship. Then hold this 3 minutes. Then it's called fractal. Couple minutes. Okay. So I go show some fractal dimension. Just one thing show the example is that you start like initiate one given length. You can divide, you can generate an infinite number of points, but never goes to zero. But all the adding together cannot go to the original length. Okay? Yeah, that's another thing. You just see that. Problem here is in all the nature have a fractal geometry, or mathematically you can prove. That means nature is not to generate the randomly, that's some design. That's doesn't show. So we have several analysis happening. This one. So we have to see. This one important concept here is even same average, same coefficient variation, we can generate all different fractal dimension values. As you see, the top sample is fractal is 1.3, bottom is 1.8. 600. You see a totally different profile. You expect a totally different physical properties. That's good. So here is another one. It's a formation test. Sample A, sample, average and standard deviation same, mean. Then question is, are two samples identical? Answer is totally no, unless the next slides. You see? So you see that the sample B is much larger, very poor formation. It's the same to mean value and coefficient variation. Okay? So this is how to calculate variable. So if you have a question, let me know later. Okay? So to save time, we skip this one. So we have some about fiber printing papers how to apply fractal dimension. I can just go next one. So we have a fiber samples, all different surface profile here. You see, the same average thickness and variation. You see you expect like all behave a different way to printing to variability. Okay? So this is how to generate from image to get the fractal dimension. Then we have correlated this fiber printing paper between the fractal dimension and surface roughness. You see that nice correlation. That means the surface roughness, mean deviation from surface roughness is highly correlated to fractal dimension. So we can move on. So we tried all different measurements, like Benson is air leak method, OS is optical, SM is a contact. You see that's good contact, much high correlation in fractal dimension. So one last thing I'll show you is fractal geometry can apply everything, particularly I said one is the surface roughness area. We're emphasizing this presentation. Let's see. Next one. Here is everybody knows the Young application wetting contangle actually control the roughness better to improve wearability. So this is very nice. We need to think twice. Why you need really smooth surface for printing coating? So basically summarize it. Another important is if you develop one optimal condition on paper grade, that does not mean you can apply to other grades, depending on your purpose and the property of each grade. Okay? So I think we can skip this. Sorry for that. Okay, that's all right.
Thank you very much, Professor Ko. Please. I see. So before we come